Hello everybody. Today we'll be talking about chapter 6. It is about current and current density and conductors. First of all, if we define the current to be a rate of transport of electric charge past or crossing a specific point, okay, or specific surface. So it is a rate of transformation for electrical charges within the conductor. The symbol I is usually or generally used for constant currents, and this I we mean the capital I letter and small I letter for time variable currents. Its unit is amperes or coulomb per second. Now, if we talk about simple DC circuits, then always Ohm's law will be used. The simple form of Ohm's law is that I equal V over R. This is very simply used in simple DC circuits. Now, this will not be the case for electromagnetics. Why? Because the electrical charge may be confined in gases or liquids. For that reason, it will not be simply just like flow of charges passing through certain conductor, but maybe will be suspended in liquid or gas, and something else that both positive and negative charges or charge carriers are present within different characteristics, even maybe confined with different characteristics. So it will not be simply deal with you will not be simply deal with Ohm's law, but in this case more importance will be given to something else, which is called J, the current density. And current density, its unit is ampere per meter square. This will receive more attention in electromagnetics more than the traditional current. Conduction current density, J. So it's time to talk about this current density as we introduced in the introduction of this chapter. This current density, J, or specifically if we talk about its type, why? Because we have another type of current density will be taken in next chapters, specifically in chapter number 13. It is a displacement current density. So you have two types of current density, JC and JD. JC is conduction current density, which depends totally on the conduction of materials, while JD is displacement current density. It is something like, if you can consider the capacitors, for example, you have parallel plates like that, okay? So imagine you have two plates opposite each other. Now you have certain current will be passing through this capacitor, but this current, we are talking about AC current. So we already know from circuit theory that for AC case, you have certain amount of current will be continually passing through this capacitor. But if you think about it, you have an isolator between both of these plates. So how could how can current pass through this isolator? Here the answer is it is not a simple current, or it is not traditional current, which is conduction current passing through conductor, because you are talking about isolator. So here the interpretation for this case is more suitable if you think about the other type of current, which is called displacement current density, JC, which JD, which is totally depend on the oscillation of the fields and whether the electric field exists somewhere, and you have time varying for this electric field or electric flux density. This will be more talking about in chapter 13. For now, if we continue, if we proceed in whatever we're talking about, okay, which is the conduction current density, it will be this one, which is multiplication between sigma and E. Sigma and E. And sigma is conductivity of materials, and its unit is Siemens per meter. Siemens per meter, and Siemens is 1/ohm. Okay. Now let's talk about the current itself. Current itself. For current, if we talk about the current, how to be calculated from current density. So in this case, it is suitable if you think about this figure 6.5. Figure 6.5 showing us certain cross-section area, maybe cross-section area of certain conductor, and you have a current density passing through it, maybe normal to this cross-section or having certain angle. Here in this case it is plotted as a general case, having certain angle with it, but as a formula, if you look at how current will be calculated, it will be differential current will be equal to dot product between J dot ds. J dot ds. So if you want the current itself from the differential current, you have to integrate both sides of this equation, and sure, the integration will be all over this cross-section area. We have an example here. In this example, saying that find the current in the circular wire shown in this figure 6.6. If the current density is J equal this amount, it is an exponentially decayed function with respect to R. So the radius of the wire is 2 millimeters. To start with such question, you have to know which formula is more suitable to be used. So we are just talking about the correct formula, or the important formula of finding, you can see here, of how to find the current from the current density. So you will be needing for dot product between J dot ds and taking the integration for it. Now applying this formula, if you want to apply this formula, you have to conclude from the geometry of the question, you have to conclude ds. So may I zoom it just to understand whatever taking place here. As discussed in the question, as shown in figure 6.6, so you have a current directed upwardly. For that reason, you have to think about ds to be a piece of, or differential area of the cross-section area that this current will be passing through. Now, if you take a portion of maybe the top or bottom of this cylinder, it will be like that. So if I just remind you of how to be calculated, you already know from previous system of cylindrical coordinate that for such case, for the top or bottom of cylinder, of right cylinder, you will have this arc, which is RD phi, and you will have this as dr. For that reason, if you want this area, you have to say ds will be equal to rdr d phi, rdr d phi. Okay, for that reason it has been assumed like that, as can be seen here. It is r d phi dr or r dr d phi, and the direction, it is obvious that direction is upwardly directed, az. After concluding ds, you have to just substitute in the in the equation of I equal j dot ds. So j is given and ds is we have just included ds from these assumptions. So we have to take a dot product between them. If you take dot product, you can see az will gone with az, and this will be remained. Directly you can take d phi, the integration of d phi separately, so it will be taken from 0 to 2 pi, and sure the answer will be 2 pi, and this 2 pi will be constant and get out from integration, and the other integration for r may be solved by part, may be solved by certain one of the methods of integration. Okay, so by using this formula by part, okay, you can solve this remaining integration. It will be some iterations for I think you have to apply it for 1 time or 2 times. Okay, at the end you'll get the answer. So the answer will be as shown here, to be 1.33 multiplied by 10 to the power minus 4 ampere. Okay, by talking about current, and previously in previous chapter we have already talking about the potential difference and voltage. Okay, so sure the all elements are ready now to talk about resistance, for example, because Ohm's law combine between these 3 terms, the current and voltage and resistance. So resistance for any material could be concluded by knowing its voltage and current, for example, or either if you have its specific resistivity, for example its conductivity, for example its sigma, you can use certain formulas to know how much will be amount of resistance. So in this section there is an assumption. Here you can see in this figure 6.7, you have an assumption that you have a certain root or certain bar like that with the rectangular cross-section area, and to be assumed that it is identical along all of this line, and its line is or its length, I mean, and its length is L. So the cross-section area is A, whatever be this value, and it will be regular. I mean, along all of this length, it will not be changed, the cross-section area. This is important in the assumption. Now, also, if you assume that this piece of conductor being connected to certain DC power supply, DC voltage source, so in this case it will be experiencing certain electric field between both sides of this side and this side, okay? Between both sides of this piece of conductor, by having this voltage, there will be certain electric field applied on both sides. Now, to know how much its value, it's very simply could be concluded to be V over L. Why? Because it is regular shape and having same cross-section area from start to end. So this assumption is correct. Otherwise, could not be used. This simplification could not be used. Now E equal V over L, and we know that from units it is correct because the units for electric field is volt per meter. Already we know that J equals sigma multiplied by E, E equal to sigma E. For that reason, if you multiply just this previous equation by sigma, you can get the equation for J. Now, assuming that the current is uniformly distributed over the area, the total current is then, now if you think about the current density as a relation between current density and the current itself, sure, the current density, even from its units, calculated by dividing the total current over a certain area, and from this you can conclude that the amount of current will be multiplication between J multiplied by A, J multiplied by A, and we have just concluded J. If you bring J here, you substitute it, you will get this. You will get this. Okay? Since Ohm's law states that V equal to I multiplied by R, hence R will be equal to L over sigma A. Okay? As previously we concluded this relation between current and voltage. For that reason, you can conclude this equation by saying voltage over current will be equal to R, and at the same time will be equal to L over sigma A. Okay, which has been concluded here. Okay, now something very important. In some cases you cannot conclude very simply the amount of current, or dealing with the current as a constant current to be flowing through all over the conductor, and even the conductor itself may be changing its area along its length. Along the length of this conductor, maybe its width or its thickness or its cross-section area will be changed. So in this case, you have to take take the amount of current from early beginning, from its formula. For that reason, maybe in some cases this relation is more suitable. And even for this case, you may not have current density, but you may have electric field instead. So from electric field you can multiply it by sigma and then make dot product with ds, and then you can calculate its resistor. Something else that about voltage itself. Maybe voltage is not given to you, maybe you are given just electric field in some cases. So for the numerator and denominator, you will be using electric field. As you can see here, you will be depending on electric field in calculating the resistance like given in this formula. You have an example now. This example saying find the resistance between the inner and outer curved surfaces of the block shown in this figure. It is like a piece of triangular cheese, lavash kiri or any type, okay, just to understand the geometry, okay. So, and this piece of cheese has been eaten, okay, from its side, okay, one of its side. Now you have this this structure as shown in figure 6.8, okay. So according to whatever given to you in this example, and the direction of the current to be directed outwardly, I mean from inner to outer. If you imagine cylindrical coordinate, I mean from inner, from z-axis to outside, or in AR, if we specifically talking about direction, directed AR in AR direction. Okay, so something else is given to you, that J is given as this. It is given to you as some kind of simplification. J is given to us, but without values, just with some symbols. It is a constant K over R AR. So here you have to distinguish between K and R. Which one is variable and which one is constant? Sure, K is constant and R is variable. Why? Because if you talk about cylindrical coordinate, which is much more suitable in this case, it is unreasonable to go to or think about spherical coordinate, because in this case is very suitable to cylindrical coordinate. So in cylindrical coordinate, how many variables you have? You have R, phi, Z. So when you are given J like that, like in this case, okay, K over R, sure, K will be certain number or certain constant value, while R is variable, and its direction is as even shown in the figure. It is AR direction. Now from J you can conclude E. How to conclude E? We already know that J equals sigma multiplied by E. So E equals J over sigma. So just divide on sigma for the given equation. The given equation will be divided on sigma to get the electric field. We are in the way to apply the last formula we're talking about in previous page, which is just depend on electrical field. So even electric field may be not given to you, but if you are given the J, the current density, so current density could be used to find electric field, then electric field will be applied to find whatever required from you. Now if you apply the formula which saying r equal to integral of E dot dl, and both of these are vectors divided by the current will be J dot ds, and J is sigma, so sigma E dot ds. As previously we're talking about this formula. So if you apply all of these things and taking into account the limit of integration, then you get a closed form for the result. Why? Because in figure 6.8 you have dimension of the given structure. You have certain specified dimension for it. From these dimensions you can get the limit for the height, for example for z-axis. You can get the limit for r, for example, and even you can get the limit for rotation, for phi. For phi you have 5 degrees. So take care about 5 degrees. 5 degrees will not be taken directly if you want to take a limit of integration. Take into account that 5 degrees will be in radian opposite to 0.0873. Okay. Maybe something very important here if we want to talk about that the calculation of potential difference. Potential difference sure will be between this side on figure and this side. Okay, both of these sides. For that reason, if you draw a straight line like that, may I just zoom it? Okay. So what will be the differential length of this? If you take piece of this straight line, it will be d something. D, which variable here will be changing? Sure, it is not phi, not z, but it is just r. And even it is not r d phi. Why? Because r d phi, if you want to take piece of this arc, it will be r d phi, but here this one is dr, and this dr will be in which direction? It will be in IR direction. So this will be the equation of this piece of of length. Now this will be dot product will be taken between this one and the electric field concluded from J, which is given to us in the example. And for the limit of integration, after performing the dot product, IR will go with IR. Just you have to think about dr here. For that reason, you have single integral. Just one integral with respect to r, and how much r? R will be changing from this point to this point, from point 2 to point 2 to 3, from point 2 to 3 actually meter. And this has been fixed for used for the limit of integration. For the denominator, take care about having the integration because you have ds. So for ds, you may have double integral. Sure, you'll have the double integral, but think about whatever you have and how much will be ds, how it is concluded to be this value. May I plot it right there, just, or I can even use the whiteboard, but I have enough space here. Okay, I'll try to plot a piece of this structure, the inner or outer side of this piece of conductor. Okay, like that. Now if you take piece of it like that, sure, may I zoom it? Sure, it will be composed of dz and the arc. The arc will be r d phi. So how much will be d? And sure, you have to take care about its direction. Its direction will be a in ar. So ds will be equal to r d phi dz ar. It has been concluded like that. And if you use it, okay, you will bring it here. Then after performing dot product, just you will this will gone with this, AR will gone with AR, and also R will gone with R. Unfortunately, you don't have dr here for integration, so you have to integrate with d phi and dz just. Okay, for that reason, just now you will think about the limit of integration. This will be for inner, this will be for outer. Before this time, you cannot judge which one or which limits will be needed if you don't know what will be decided by ds. What will be decided by ds? Why? Because in some cases, for example, if I ask you or if I give you, for example, this J or the direction of current to be not directed in direction of AR. For example, if I give you in direction of AZ to be certain value, J to be certain value, or maybe even as a function of R or function of Z or whatever, okay, or just a certain number. But the important thing that if I give you in another direction, so in this case you have to take another ds. Why? Because the cross-section area of that piece of ds, which is the current, is normal to it. Okay, so in this case you have to, may I zoom this side? I know it is somewhat difficult to do that, but I'll try to do my best. If you take this piece of conductor like that and try to think about this piece instead of taking this piece of area, okay? Now what is this dimension? It is dr. And also this one, it is r d phi. So who can tell me how much will be? How much will be? And its direction will be upwardly to AZ, and we will say ds equal to r dr d phi what? AZ. Okay, so be careful and look at whatever you have, because for same geometry, maybe if the direction of current changed, everything will be changed in the solution. Now it is time to talk about something very important, which is current sheet density. And for current sheet density, from its name, it's not current density, it is current sheet density. As a unit, for current density, previously we talked about J to be ampere per meter square, while here for current sheet density it is just like having a current. If I talk about specifically about certain sheet, for example this piece of sheet, okay, so from its name to be current sheet density, that you have a current being divided or distributed all over this sheet, for example, a piece of sheet. Now, thinking about certain current being distributed all over here, okay, and instead of having a current being distributed like that on a certain cross-section area. So if you have a current flowing through certain sheet like that, you will not have cross-section area. This current will be flow in, okay, but you may have certain length. Your current will be distributed all over this length. So even this sheet may be folded like that. If I fold it like that, it will be like a cylinder, for example, like a certain hollow cylinder. If you have such case, hollow cylinder, and you have certain current just flowing through this cylinder on the surface of it, okay, not you have hollow, okay, you don't have any conductor material inside, so your current will not be divided all over this area because this area is hollow, but instead it will be divided all over this circumference of this cylinder, okay. And if it is not cylinder, just a certain sheet, the current will be divided on this length, for example, or this length, depend on its direction. Let's get back to the section now. Just like whatever you're talking about, he's talking about this figure 6 number 6.9, as I discussed here on this piece of paper, that if you fold it, it will be like a cylinder, and your current will be flowing through this cylinder. For that reason, to calculate the amount of current sheet density, you have to divide the amount of current over the circumference. How much is the circumference for a cylinder? It is 2 pi r. For that reason, without any doubt, it will be K will be equal to A over 2 pi r. Maybe strange for you why K is used just for distinguishing between K and J. So K is ampere per meter, while J is in ampere per meter square. Okay, so both of these are densities, but different. This is current sheet density, while this is just current density. I mean, K is current sheet density and J is current sheet is a traditional current density. He said, in general, for any contour. Why? Because here you may have certain cases being irregular. Not always you will have a rectangle and circular shape and a ring and certain loops. Okay, you may have any irregular shape, so you will be you will deal with contours. Okay, contours. As discussed previously in the starting of this section, that K will be calculated by dividing current over certain path. So if you want to get current back from the current sheet density, you have to think about that current must be equal to K multiplied with differential length. If you have differential length, you will get differential current from it. And if you specifically want to find current itself, you have to take integration for K dot dl. And here there is a mark here that integration will be performed along a certain contour For that reason, this letter C, you can see here a letter C as a notation for whatever we're talking about. The integration will be taken over or across certain contour. We have an example number 5. A thin conductor sheet lies in the z equals 0 plane. For limit of x to be from 0 to 0.05 and IY directed current. You have a current directed in y direction. Its value, amount of total current, is 25 ampere, is sinusoidally distributed across the sheet with linear density 0 for x equals 0 and x equal 0.05 meter, and maximum at x equal. So from these informations or these values, okay, you can guess its function. Why? Because it is sinusoidally distributed, not uniformly distributed. As shown in this figure, you can see that it is sinusoidally distributed. He asked for the value of K. Obtain an expression for K. How to find an expression for K? And also, I think it is required to find even the value of K as a magnitude. From the given information, you can conclude that it is sinusoidally distributed, and it is sine function. So you have maximum value. This is representing maximum value, small k, and this is the function sine. 20 pi x comes from the sinusoidal distribution of the function, so you can calculate its period by thinking about 2 pi f multiplied with x, and f equal to 1 over t, but you don't have t here, t representing the length of the period of the cycle. Here you have half of the period being given to be 0.05 meter. Okay, so from those you can discuss it here. Just sine 2 pi over the period. Okay, over the period, multiplied by x. I mean, all of these is the angle of that. So how much period? I am intending not to type t because you don't have t here. It is a space function with respect to distance. So you have this for half of sine cycle, multiplying by 2, you get the complete period. How much will be? It will be 0.1 meter. Okay, so you'll think about 0.1 meter to be 1 over 10 as the denominator. For that reason, 10 will get up. 2 pi multiplied by 10 by x, and this sure will give you 20 pi x. From knowing this equation, and previously we already know that I equal to closed integral all over contour k dot dl. Okay, so this could be used to find the amount of k. Okay, you already know how much the current is. Current is given to be 25 amperes. From all of these information, you can get the big value of the current sheet density. Now we get here, it is time to talk about something very important in this chapter, which is section 5.6 about conductor dielectric boundary condition. If you think about a certain case when you have a conductor, okay, a conductor with having interface with certain dielectric, and the dielectric may be any type of dielectric, even maybe the pure air, for example. So in this case, if you want to think about what will be the behavior of electromagnetics, if electromagnetic field between the conductor and dielectric, here there is a certain assumption taken place. For example, some of these assumptions is the conservative of the field, or may I introduce it in a more simpler way? Just I remind you about Kirchhoff voltage law, for example. Kirchhoff voltage law. In Kirchhoff voltage law, if you take a certain closed path to combine or to make summation for voltages, sure the answer will be equal to 0. So for that reason, here in somehow it is the same thing, saying that because the electric field is a conservative field, as we mentioned, okay. So the line integral of E dot dl. What does E dot dl remind you? E dot dl equal to the voltage, as you know, from B to A, and you have minus here, you have V A to B. So E dot dl remind us about the voltage, and same as whatever we're talking about, you can think about just applying a KVL on a closed path. Now, where this closed path we're talking about, the closed path here in this case will be assumed to be you have 4 points. If you assume that you have 4 points, for example, 2 of these points located inside the conductor, 2 other will be located outside the conductor within the dielectric, for example, as shown in figure 6.11. So from 1 to 2 you have a certain path, from 2 to 3, then from 3 to 4, then finally from 4 getting back to 1. Now constructing this long equation and just thinking about certain assumption, that if we assume that each of points 1 and 4 and as a distance, 1 with 4 and 2 with 3, okay, if you try to shrink this distance, if you try to minimize this distance, if you try to take dl to be very close to 0, so due to having dl very close to 0, which term will be cancelled? The term of integration, this one, the second and the fourth one, as mentioned here, 2 to 3 and 4 to 1 are now permitted to approach 0. How to approach 0? Because the path length depend on our assumption. So we can assume that this distance very close to 0, and we are trying to take a certain case very close to the interface between both of these different materials. We are talking about conductor and dielectric material. look here saying that keeping the interface between them without losing the interface between them. Something else for the third term also third term could be considered to be equal to 0. Why? Because within the conductor there will be no any electric field confined. Okay, there will be no any existing for the electric field intensity, so not due to having DL equal to 0, but having E to be equal to 0, this term will be, all of this term will be equal to 0. So the remaining one will be just the first one. Just the first term will be kept here, and this because the all other terms are gone. For that reason, the last term will not survive. The last term also will be equal to 0. Why? Because our equation, originally our equation is equal to 0. Now, thinking more specifically about this case of having integral from 1 to 2 E dot dl, and thinking about this path between 1 and 2. So may I zoom it? What do you think about the existence of the field? Which kind of field you will have here? Sure, you will be talking about E tangential. E tangential. Why? Because you are taking dot product, okay, here between E and dl. So if you think about other than E tangential, then the dot product will be 0. The answer will be 0. So the non-zero product will be just in that case when you take dl dot product with specifically with E tangential. But even if you perform this with E tangential, the result will be equal to 0. Why? Because we depend on the result of equation. Originally the equation, we know that it is equal to 0. Now it is time to conclude something. If you examine this equation, the resultant equation, what does make it equal to 0? This one or this one? I mean, does dl equal 0 or E tangential equal to 0? Sure, dl will not be equal to 0 because we haven't assumed here that this distance is very close to 0. But if this not equal to 0, sure the other one, the other one will be equal to 0. From this assumption and this conclusion, we can conclude that E tangential, and by the way, D tangential also, the electric field and the electric flux density both will be equal to 0. Now, this is the important thing in this boundary condition. If we want to think about the normal component, certain assumption will be done. This assumption is by having a certain right cylinder. If you think about a certain right cylinder and applying Gauss law, we are talking about figure 6.12. So if you take this case, figure 6.12, and 6.12, we have a figure representing the interface between the conductor and the dielectric, and having a right cylinder exactly at the interface between them, then trying to apply Gauss law there, and the Gauss law sure you have to think about this cylinder taken. This cylinder, you have three sides. You have three sections, I mean top and bottom and side. Okay, so on the other side for Q enclosed, I will just maximize this plot just to understand whatever taking place here. Okay, so you will have here exactly at that level, okay, where the interface exists, you'll have certain area. So may I use the whiteboard also here, and this, it is more suitable to, okay. Now this is the application of Gauss law, and you have three parts. The integration will be divided into three parts for top and bottom and side. And if you think about the bottom, for example, bottom will directly gun. Why? Because bottom is inside the conductor, and inside the conductor, previously we were talking about it, that you will not have any existence for the field inside the conductor, so the bottom will gun. Bottom will be equal to 0. If you want to think about side also, side will be equal to 0. Why? Because for the side, may I plot it here or even here? I can zoom this one. If you take a piece of side, for example here, this is ds, and if you want to think about certain d, this d will not be a normal component, but it will be tangential component. And previously we concluded that there is no tangential component from the conclusion of made previously. For that reason, dt equals 0. If dt equals 0, then what? May I get back? It is here. If dt equals 0, I mean what? The whole amount of the third term will be equal to 0. For that reason, you will have just the integration. Let me use the whiteboard. D dot ds, okay, on the top. On other side you have what? On other side you have Q enclosed, which is Q enclosed as plotted here. You can see what will be Q enclosed. It will be just over this area. So I can say that it is close integral rho s ds, and sure the integration of this will give you this area. Okay, now on the other side, on the left side of Gauss law, again you will have d to be constant, will get out, and what will be the result for this? For the top, I'm talking about top, you will have this area. So this area, you can name it even area top. Okay, so it will be area top. If you think about area top and the other area, rho s, the other area, sure both areas are the same. Why? Because it is very clear this area and this one, this area, okay, they are same area, because one of them at the middle of right cylinder, the other one at the top of right cylinder, and you are talking about right cylinder having continuity for the cross-section area, so both area will gone, then you will conclude something very important, that D will be equal to rho S. Which kind of D? Which kind of D? If you zoom it, sure it will be D normal. But here we are talking about its magnitude. There is no direction specified here, so this is the important thing has been concluded here. And now may I summarize whatever concluded here, that E tangential equal to D tangential equal to 0, and D normal, but D normal here is this, okay, will be equal to rho S. You can solve example number 7 very easily. He said that you are given electric field to be this value. Find the surface charge density at that point. Okay, so the electric field density, as mentioned, at a point on the surface of a conductor is given by this value. So at the surface of conductor, meaning that at that surface of conductor there is a contact between or interface between the conductor and air, for example, or because the traditional free space or air is considered dielectric, not just the case of having certain Teflon or having certain for example specific material for dielectric. I mean what? In this example it is indirectly saying that there is an interface, because he's talking about a conductor and a certain point at the surface of that conductor. So sure, at this point there is a contact between dielectric and conductor. For that reason, boundary condition must be taken into account. And sure, if he asked about the amount of charge density, we know that we have just derived this formula to be D normal equal to rho S. D normal equal to rho S. But don't forget, you are not given D, you are given, in this example, you are given electric field. So from electric field, if you multiply it by epsilon naught, why epsilon naught? Because nothing mentioned about any type of conductor other than the free space or air. Okay, so epsilon naught multiplied with En equal to Dn. This will be deciding the amount of rho S. But take care, all of these vectors italic form, meaning magnitude. For that reason, you have to take magnitude for the given electric field. In this example, then it will decide the amount of charge. But there will be a certain ambiguity, meaning that the plus or minus will not be specified. For that reason, there is two possibilities, maybe plus, maybe minus, must be taken into account. The last thing in this chapter, something very interesting and very important, which is figure 6.13. Figure 6.13 talking about certain case of having a point charge, positive point charge at the center, and this positive point charge surrounded by a certain spherical shell, as shown in figure 6.13 A, as shown here. Okay, so something very important, that the electric field around this positive charge will be given by this formula. by this formula. Okay, and whatever taken place or whatever occurred on the spherical shell is discussed in figure B, or shown in figure B. The amount of electric field intensity, or if you think about Coulomb force produced by having this charge at the center of this sphere, will attract the negative or electrons, negative charges or electrons to the inner surface, as talking about here. Okay, so the positive charge at the center will attract, make attraction for the electrons to get down to the lower surface of this shell. As a result, when these electrons get down, they will lift certain holes or positive charges on the upper surface. For that reason, you get a negative charge here, rho S1, and you get positive charge on the outermost surface, and then the outermost surface charged with, as a result, with positive charge. The all charged or distributed charges will be working together to emit or to generate another flux in the same amount of that flux coming from the original one. Meaning what? Meaning, just if you think about the same system, if you have a source of light at the center, at the center of at the origin, and you have a spherical shell made of glass, for example, which is transparent for the light, and this light at the center, at the origin, will be starting to emit lights. So these lights will be penetrating this spherical glass and getting out, even just like this shell not exist. Why? Because it is transparent. Something like that will be taking place, but not due to having penetration of this flux through the conductor shell, but due to attraction, the negative, the electrons in that conductor, that shell, downwardly to be collected on the inner surface, and the outermost surface will be having a positive charge distribution, and the outermost charge will try to emit again, just like done previously for the original point charge. There will be emission for flux from the outermost surface, and the flux will be seemed like continue. But this continuity will not be due to penetration, but due to this phenomena. By this, by talking about this phenomena and this section, we have finished the most important thing in this chapter. The important thing that this chapter has not been taken completely. For that reason, even for solved problem, the whole solved problem will not be required from you. As you can see here, solved problem started with 6.10, and maybe certain this 6.11, 6.12 selected questions. For this lecture it is enough, and the solved problem is already solved step by step. If you have any question, So write to me and ask me in coming meeting. Until that time, take care and thank you for watching, and see you.